This video will be about orbital notation and Hund's rule, and also I'll be telling you about Pauli exclusion principle and the Lewis dot structure, how to draw it. So here is oxygen, and I've written out the electron configuration. Now let's use this to find out the orbital notation. So with orbital notation, you might see boxes or lines. They're both common to see. Maybe you can also find circles. So I've drawn boxes, and these boxes are orbitals. Each individual one is one orbital, and orbitals can hold 2 electrons in each of them. And so for the first thing, before we begin, remember that in the quantum numbers, the electron is shown by spin. And the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. And the only way, if they are in the 1s sublevel, the only way for them to differ in quantum number is the spin. So, which is ms, and it could be plus 1/2 or minus 1/2. And to show this, we use arrows in the orbital notation. So the up is plus 1/2, down is minus 1/2. And that shows that we have 2 electrons that have different spins. The one pointing up, we call it spin up, and the one pointing down, we call it spin down. So let's fill out the rest of the orbitals. Alright, so we filled up the rest of the orbitals now. But as you can see in the p sublevel, the 2p sublevel, there's one orbital that is not filled with anything. This is where the Hund's rule comes in. So the Hund's rule states that if there's an empty orbital like this one, an electron would prefer to be in this empty orbital before pairing up with another electron. So that means that this electron right here will actually want to be here instead. So this is the proper way of writing the orbital notation for oxygen. Now, the second part of Hund's rule states that the first electron in the first orbital of a sublevel, let's use this, will determine the spin of the unpaired electrons, these two. So as you can see, this one's spinning up, and these two are spinning up also. So if I switch this to spin down, then these two will also have to spin down. Now, how do we use this to find the Lewis dot structure? So we have oxygen, that's the elemental symbol, and the Lewis dot structure will only show the valence electrons. And the valence electrons are the electrons in the highest energy level, and for this case it's the second energy level. So we have 1, 2, 3, 4, 5, 6 electrons, valence electrons. So let's draw them in the Lewis dot structure. So usually in a general dot structure, we'd have the s orbital here, or s sublevel. So we have 2 electrons here, the s sublevel. And then in the first orbital for the p sublevel, it would be up here, 2 electrons. And then 1 unpaired electron here. And then the last p orbital would be here. But we don't actually have to stay in this structure. We can move the orbitals around, or the electrons. So we can actually write it also like this, or like this, And those are all Lewis dot structures. So now we've learned how to write orbital notation and use Hund's rule and also draw Lewis dot structures.